All right, so I'm going to try to post this as one of the videos that shows up now that we're doing something new. So you were looking at a system of silicon dioxide and Pyrex and looking at helium as it was diffusing through this system. So this is a binary system now of a thin film of silicon dioxide over a thicker film of Pyrex. This was 0.5 millimeters, so 500 microns, and this, I believe, was 100 microns of silicon dioxide. Uh, 100 microns is 0.1 millimeter. And so we gave you a few diffusion coefficients. This had diffusion of helium through SiO2, and we'll just say this had the diffusion of Pyrex, helium and Pyrex. We'll do a P. And we were looking at having some pressurized helium on this side, so the fraction of helium is 1 here. And it's also common to write gas fractions, especially if we're looking at mixed gas phases, as a Y instead of an X. Here we're looking at a gas diffusing through a solid, so we'll use the X as the fraction of helium in the solid. With gas phase fractions, it's also very common to use a Y as the fraction. So we also had that the fraction out here was negligible. And you needed to find what the total flux was of helium from the inside of the system to the outside of the system. So we wanted to know what was this molar flux of helium. And so what you guys did was you set up a resistance network. You said, well, if there's going to be some driving force being this fraction of helium, we have a high concentration of helium on one side of this barrier and a low concentration of helium on the other side of this barrier. So we have a strong driving force, and there must be some sort of resistance to that driving force. So we looked at this as a resistance network. And then each node where we would say maybe measure a voltage would be a concentration. So we would have XHE naught, say, is the value of 1. We could have some fraction of helium at the interface. Let's just call this I for the interface. And then a 0 fraction of helium on the outside. Final. So we have in original, the fraction of helium naught is 1. We have some fraction of helium at the interface and some fraction outside. And we could write this, then the driving force is the actual change in the concentration. But what we have is going to be N flowing through. So instead of a current flowing through, we have a certain number of moles flowing through. That's analogous to the current flow in electricity. And then we'll have, instead of an electrical resistor, we will have some mass resistance, right? And you found this mass resistance was almost exactly the same as a thermal resistance. Instead of L over Ka, you had something like the mass resistance being L over the diffusion times the area. So if we apply this to our system here, what we're seeing is this length would actually be the thickness, and The diffusion coefficient would, of course, be whatever the diffusivity is in the material, and that changes by an order of magnitude between Pyrex and silicon dioxide. Silicon dioxide has an order of higher diffusivity. It's much easier to transport through the SiO2. It's typically, if you deposit this with a thin film deposition tool, it's going to be amorphous and porous. The diffusivity should be much, much higher through some deposited silicon dioxide than some pure Pyrex. Which is true, which is what we do see. The order, we have about 4.5 times 10 to the negative 15 for the diffusion coefficient through Pyrex, that is meters squared per second. And for silicon dioxide, for the amorphous material, I believe it's about 4 times 10 to the negative 14. So you get an order of magnitude difference in the diffusion coefficient. And so you see you get an order of magnitude difference in the resistance to the mass transport as well.